In section 4.4, we delve a little bit deeper into factoring polynomial functions. So, same question as previously. I'm given this polynomial, and I want to factor it completely. And it's a cubic, so I know there's going to be 3 factors. So when I graph it, I get something that looks kind of like this. Looks like this far left-hand branch is going through -7, and when I check it on the table, it is indeed going through -7. But these two go in between 2 hash marks or in between 2 whole numbers, so graphing it really doesn't give me much help there. So what I'm going to do is use this -7 to reduce this equation to a quadratic, and then I'm going to either factor that or plug it into the quadratic formula. So let's get started on that. I set it up for synthetic division. Bring the 1 down, multiply by -7. Add them together, multiply by -7. Add them together, multiply by -7. And it is indeed a factor, which we knew already. So what that tells me is x plus 7. And remember, going between zeros and factors, we're changing signs. X plus 7 is a factor of this. And furthermore, I have this when I factor it on my first step. Now all I have to do is factor this. And you have 2 methods to do that. One is to plug it into the quadratic formula and get the zeros and convert them back into factors. The other way, since we have a minus here, is just factor using square roots. So we've now completely factored this polynomial. One of the important things you need to take away from this section is that irrational and complex zeros occur in conjugate pairs, which sounds complicated, but it's really not too complicated. What a conjugate is the exact same number with the imaginary part or the irrational part changing sign. So if that's a complex number, that's its conjugate. If that is one of the factors, I'm guaranteed that that's a factor. So if I have a factor of 9i, I automatically know I have another factor of -9i. And it works the same for radicals. If I know I have a factor of radical 5, I know I have a factor of negative radical 5. If I know I have a factor of 2 plus radical 3, I know 2 minus radical 3 is also a factor. And the next thing we touch on is the potential rational zeros, often called Descartes' rule of signs after its inventor. Okay, what you're going to find with this are potential rational zeros for a problem. You're not guaranteed that the numbers you find are zeros. It's just that if there are rational zeros, they are going to come out of this list. And to find this list, we just take all the combinations of factors of the last number over factors of the first. So in this particular case, the factors of the first number are just 1. The factors of the last number are 1, 2, 4, 8, or 16. So all we're going to do to find the potential rational zeros is put our little plus or minus out there. And actually your MATLAB will do this part for you. You just have to fill in the blanks. So all the factors of the combinations of these factors over this factor, so 1 over 1, 2 over 1, 4 over 1, 8 over 1, or 16 over 1. And then all you have to do is simplify. And again, these aren't guaranteed to be zeros, but you do know that if you have a rational zero for this equation, it will come out of this list. So let's try it with something slightly harder. Here, the factors of the first number are 1 and 2, and the factors of the second are 1, 2, 3, or 6. So the combinations of these numbers over these numbers would be 1 over 1, 1 over 2, 2 over 1, 2 over 2, 3 over 1, 3 over 2, 6 over 1, 6 over 2. And now all you have to do is simplify and remove repeats and try to put them in some sort of order. So we'll start with the 1/2, and it might help to cross them off. Let's see, let's try 3/2 next. And 1 seems like it comes next. But 2 over 2 is also 1. So we'll cross that one off too. Then we have a 2. And then we have a 3. But 6 over 2 is also 3, so we'll get rid of that one as well. And then 6 over 1, or 6. So these are the potential rational zeros for this equation. And the last thing you're going to do is find a polynomial with the given zeros. And the only hard part about this is you actually have to multiply it out. So I know a polynomial with these zeros. It's that. And now we just have to multiply it together. So let's multiply the imaginary numbers together first, simply because it's going to be easier when I do so. So foiling it out, x times x is x squared plus 9xi minus, so it's a 9, minus 9xi minus 81i squared. The middle terms cancel each other out, and the I squared just changes the sign of the number it's attached to. So this is actually x minus 4, x squared plus 81. Alright, now we just need to multiply these two together. And you'll notice my imaginary numbers disappeared completely. That's what happens when you multiply conjugate pairs together. The irrational part or the complex part, imaginary part, goes away, and you're only dealing with real numbers. So let's multiply these together. So x times x squared, x times 81, 4 times x squared, and negative 4 times 81. Let's see what the calculator says on that. Negative 324. And let's just put that in order. And we're done.